Welcome to a discussion of sequences. A sequence is just a list of terms. The terms could be anything. So far we've seen sequences of numbers, sequences of intervals, points, vectors, mathematical statements, sets, and so on. And later on we'll want to talk about sequences of functions, but right now we want to discuss just sequences of numbers, particularly real numbers. The first example listed here is a sequence of numbers generated randomly by the roll of a die. This is a deterministic sequence called the 2 Morse sequence. See if you can spot the defining pattern here. Just a sequence of zeros and ones. Sequences do not have to have distinct terms, certainly. This sequence is defined by an explicit formula for the nth term, as shown. And this sequence is generated by a recursive formula rather than an explicit formula for the nth term. This sequence is determined by taking 1/3 for the first term, and thereafter each term is determined by applying a certain quadratic function to the previous term. Now every sequence can be thought of as a function defined on the natural numbers, or perhaps on the non-negative integers, or some sequence of integers. However, in the next to last example, you could think of this function as the restriction of a function f of x equals 1 over x squared plus 1, just restricted to the non-negative integers. And why would you bother restricting to the non-negative integers? But in the last example, this recursive definition is very different from that, because you can't really talk about ax for a general real number x. It's really just something that has to be defined for integers. So the well-ordering of the natural numbers is what allows us to do that, to define a sequence recursively in a way that has no extension, really, to the real numbers. Now one could talk about finite or infinite sequences of anything. Here we just talk about countably infinite sequences of real numbers. In this setting, any function from the natural numbers to the reals can be thought of as a sequence. And we call an the nth term of the sequence, and n is its index. Sometimes the entire sequence is denoted with parentheses around it, and sometimes we also decorate it as shown with a subscript n element of natural numbers, just to remind us the range of indices. The sequence is bounded if there exists a number m such that the absolute value of each term is at most m. So this is the previous notion, really, of the bound for a set, as applied to the set of all terms of the sequence. A sequence is increasing if each term is less than or equal to the next one. This is also referred to as weakly increasing, since all the terms are less than or equal to, not strict less than. And similarly, we have decreasing sequences, which is to say, again for emphasis, weakly decreasing. If a sequence is either increasing or decreasing, then we call it monotone. We say the sequence an converges to a limit L if this condition holds, that for every positive epsilon, the terms get within epsilon of the number L beyond some point. Precisely, this last phrase means that there exists a capital N, depending on epsilon, such that a sub n is within epsilon of L whenever little n is bigger than big N. Here are 3 ways to write this statement in symbolic form. If a sequence doesn't converge, then simply it diverges. So for example, the sequence 1 over n, as shown, converges to 0. And here is a sequence of rational numbers converging to pi. Here's a sequence converging to 1. And the sequence of natural numbers itself diverges. Also, this last sequence diverges. We have terms alternately plus and minus 1. And this is different from the previous example. It diverges again, but in a different way. Because here the sequence is bounded, but they don't approach any limit. It just oscillates. That's another way the sequence could diverge. As a very first proof about limits of sequences, as an easy exercise, let's show every sequence has at most one limit. This means that if there's a limit, we can talk about the limit rather than just a limit for the sequence. Suppose, on the other hand, that a sequence has two limits, L and L prime. Take epsilon to be half of the distance between those two limits. And now I'm going to assume that epsilon is positive and try to get from that a contradiction. Beyond some point in the sequence, the terms are within epsilon of the first limit. And beyond some point in the sequence, possibly a different point, the terms are within epsilon of the second limit. Now we can take little n to be bigger than both capital N and capital N prime, in which case the nth term is within epsilon of both limits, L and L prime. This is where you can get the contradiction. To do that, use the triangle inequality. The absolute difference between L and L prime can be rewritten using what we know, what we've seen with the triangle inequality. Those two terms on the right-hand side are bounded by epsilon plus epsilon, which is 2 epsilon. And look at the way epsilon was defined, and that shows you we have a contradiction. So at most one limit for any given sequence. Here is another basic result, also very easy to prove. Every convergent sequence is bounded. Proof: suppose a sequence AN converges to L. Then beyond some point in the sequence, all the remaining terms are within 1 of L. By the way, this kind of step is a very telling thing that if a student can do this, they're starting to get the idea of how to actually use the definitions. This is important, to not just memorize the definition and recite it, but to actually use it. And here when you say, for all epsilon, it's not going to be very helpful until you can recognize choosing an epsilon will give you something that you can actually use. By the triangle inequality, we have this bound on the remaining terms of the sequence. They're all, at most, absolute value of L plus 1. Here, by the way, are the details of that last argument in which we've used the triangle inequality. And by the way, I guess when I said less than or equal above, I could have said less than, but I don't care. Now, there are only finitely many terms with little n less than or equal to big N. So you can take m to be the maximum absolute value of those terms. You're going to get a finite number there. And at this point, you have bounded the first few terms of the sequence, and you've also bounded all the remaining terms of the sequence. And if you take the maximum of those two bounds, then you get a bound that applies to all the terms of the sequence. And then we're done. Notice that there was a somewhat arbitrary choice here of epsilon taken to be 1 early in the proof. And we could have made a different choice there, like 0.1 instead of 1. It's best to make your choice as simple as possible, but it does need to be a specific choice there to make this ideal work. The simpler and the more concrete the choice is, the more readable your proof will be, which again is the goal of a proof. If it's going to convince somebody, it has to be readable and understandable, as simple as possible. Now here, we're ready to tackle a slightly more substantive result, the monotone convergence theorem. We know that convergent sequences are bounded, so unbounded sequences diverge. But the converse of what I just said is not true. Bounded sequences do not necessarily converge. I showed you an example earlier, 1 minus 1, 1 minus 1, 1 minus 1, etc. is a bounded sequence which does not converge. I also showed you an example of an increasing sequence that does not converge. The sequence of integers is an example there. But if you put together those two things, if you have a sequence that's both increasing and bounded, then it does have to converge. Also, a bounded decreasing sequence must converge. And together that's saying every bounded monotone sequence converges. So remember that monotone means either increasing or decreasing. This theorem is going to require the completeness of the real number system. So we'll use the least upper bound property. For our proof, let's suppose that an is increasing and bounded above. In the other case, it would be a sequence that's decreasing bounded below, and that would be exactly similar to this proof. Now the set of terms of the sequence is non-empty and bounded above, so by the least upper bound property, I can take capital M to be the supremum of that set. So we talk about a supremum of a set. How does that translate into a limit for a sequence? That's what we have to show, is that the sequence actually converges to this capital M. As usual, let epsilon be positive. Since m minus epsilon is less than m, by definition of least upper bound, this number is not an upper bound at all for our sequence, which means there has to be a term of the sequence that's greater than m minus epsilon. And now for all little n greater than big N, we have these two inequalities. The first inequality holds because the sequence is increasing, and the second inequality holds because capital M is an upper bound for the sequence. So we have this inequality where the right-hand side is less than epsilon. Congratulations! We just managed to show that by definition the sequence converged to M. A little notation that's often used in place of the horizontal arrow, which is generally for writing limits. Some authors or books will indicate convergence of a monotone sequence by this diagonal or vertical arrow. In the increasing case, you say an converges to m. You can write it if you want to by saying up arrow to m to say it's increasing to m, or down arrow m to say it's decreasing to m. Here is some useful language when talking about limits and other properties as well. I believe this language already started to slip into my presentation, but let's put a spotlight on this one. We'll say a property, Pn, holds for all sufficiently large n, if there exists a capital N such that the property holds for all little n bigger than that capital N. By the way, this could be a real number x instead of an integer n. So it could be taking sufficiently large integers or sufficiently large real numbers. It's saying that some property holds beyond some point. Here is a symbolic way to say that. We use a double greater than sign to say little n is sufficiently large. How big? We don't know exactly or explicitly, but beyond some point. Let's look at some contexts in which this language is useful to express something in a concise way. One fact about sequences is that its limit, if there is one, does not depend on the first 10 terms. It does not depend on the first 100 terms, or whatever. We point out that if two sequences have the same terms for n sufficiently large, then either they both diverge or they both converge to the same limit. And we could write down a proof of this, but it would be even shorter than our short proofs from the early part of the video, so I'll leave that for an exercise. Here's an example. The sequence of terms n squared over 2 to the n looks like this. Now, strictly speaking, that's not a decreasing sequence, but increases for the first 3 or 4 terms, and then after that, it's decreasing. So as far as your theorems go, you might as well just think of it as a decreasing sequence, because beyond some point it is. because the sequence is decreasing for all sufficiently large n, and the terms are all positive, so they're bounded below, then you can apply the monotone convergence theorem. It has a limit. But to use the monotone convergence theorem, since it's not strictly a decreasing sequence, you just point out, yeah, but it's decreasing beyond some point. It's decreasing for n sufficiently large. And that gives you what you want.